This is Formal Methods Lecture 14 Recap. The topic for today is Leibniz as an axiom. Okay, so the axiom 3.83 is E equals F implies E with Z replaced by little e equals E with Z replaced by little f. And this form of the axiom uses a slightly new notation that we have for textual substitution, which is shown here. E with a superscript little z and a subscript capital X means E with Z replaced by X, where Z is a single variable or list of variables and capital X is an expression. Okay, so this notation makes it a little less cumbersome to write down the theorems in this subsection of Chapter 3 on Leibniz as an axiom. Okay, so let's review a little bit what inference rule Leibniz is. You should recall that an inference rule is a rule that we use in the step of a proof to go from one line of the proof to the next line of the proof. One of the tools that we use, we have 4 inference rules, and one of those is inference rule Leibniz. And our inference rule Leibniz says that expression X equals expression Y. If that is true in all states, then we can conclude that any expression with Z replaced by capital X is equal to that expression with Z replaced by capital Y. And we commonly call this substituting equals for equals. Now, first let's get used to the notation. Do you see how to write inference rule Leibniz using this new notation? So give it a little thought here, a little bit of a thought, and here it is. Here is the same inference rule Leibniz, just using this little abbreviation. See how much more concise it is. E with Z replaced by X equals E with Z replaced by Y is the conclusion of the inference rule. Okay, now, so that's one thing about Leibniz as an axiom. It's the notation that's slightly more concise. Now, another thing about inference rule Leibniz is that we have, in contrast to most of the other theorems and axioms that we have discussed in propositional calculus so far, we have been dealing with Boolean expressions. But notice here that it's not in 3.83 axiom Leibniz, it's not little e equivales little f, it's little e equals little f. So we have an equals here, and it's not E with Z replaced by E equivales E with Z replaced by f on the right hand side, on the consequent of the implication. It's E with Z replaced by little e equals E with Z replaced by f. So we have equals here instead of equivales. So now why is that? That's because this axiom Leibniz not only applies to Booleans, but it also applies to numbers and sets and other mathematical quantities. You should recall that one of the differences between equals and equivales is that equivales is always between two Boolean expressions. It works only for Booleans, whereas equals works for Booleans and numbers and sets and other mathematical quantities. We will even see that equals applies to between two programs next semester. All right, so those are the two main differences between axiom Leibniz as an axiom, and the inference rule. One is the notation that we commonly use with the Leibniz as an axiom, and another is that we're talking about equals between numbers, whereas usually when we use our inference rule Leibniz, we are using equivalence, equivales, when we go from one step of a proof to another, one line of a proof to the next line. All right, so let's do an example here. Suppose that the expression capital E. Now, do you remember what the definition of an expression is? Aha! Do you remember? Remember the first thing? It's either a constant or a variable is an expression, and then and etc. Right? we had, if capital E is an expression, then open paren, capital E, close paren is an expression. And then we had a definition of a unary prefix operator, and then we have the definition of a binary infix operator. So here we have, this is an expression, we have two variables and a binary infix operator. So let's suppose that the expression is x and z, where x and z are variables. All right, so now to apply this, if E equals F, then what does that imply according to Axiom Leibniz? Can you work this out? I'll give you a minute. So if E equals F, then what does that imply? Well, it implies that expression with z replaced by little e is equal to that expression with z replaced by little f. Well, what is that expression with z replaced by little e? It's x and e. And what is that expression with little z replaced by f? It's x and f. So if E equals F, then x and E must equal x and F. All right, so there's one example of the use of Axiom Leibniz. Now that from that one axiom we have these all these different theorems. We have 3.84 substitution, and there's A, B, and C, and then we have 3.85 replaced by true, 3.86 replaced by false. Each of those has two parts, A and B. And 3.87 and 88 are other little variations. And we have a Shannon theorem down here, 3.89, and an additional theorem that I have included that's not in our textbook, but which I think should be as a theorem, is 3.89.1, which is the basis for case analysis, which we will learn later. Okay, so let's do a little proof here. We are going to prove 3.84a, all right, and we will use obviously 3.83 Axiom Leibniz as one in part of the steps, one of the steps of our proof. So what does 3.84a say? It says that if E equals F, then an expression E with z replaced by little e must equivalve E equals F and expression E with z replaced by F. All right, now what we're going to do with this, how we are going to prove this theorem is we are going to start with the whole thing. We're not going to start with one side and get it to the other side. We're going to start with the whole thing. Okay, so we have to get this equivalent to a previously proved theorem, right, which is probably going to be 3.83. That's probably how we're going to work. We're going to work our way up to that. Now this first step might not seem intuitive. We're going to kind of have to pull a rabbit out of a hat here. So let's do it. The theorem that we are going to use in the first step of this proof is 3.62. Okay, so let's take a look at 3.62. Now, before we go back and look at that now, let's look at the format we have. So what do we have here? We have E equals F and something equivalves E equals F and something else. So do you see the format there? I mean, do you see the form of that? We have P and Q equivalves P and R. You see, and the P is the same in both. All right, so let's take a look at 3.62. Actually, we proved 3.62. I don't know if you remember that or not too long ago. All right, so now look at 3.62. Do you see on the right-hand side of the equivalence we have P and Q equivalves P and R, right? So what we have is the right-hand side, and so what does that equivalve? That equivalves what we have on the left-hand side. Do you see? So what we're going to do is we're going to take 3.62, and we have P and Q equivalves P and R. We're going to take that P out, and that P is going to imply Q equivalves R. Now, I've been showing you these proof steps with, blue and red underlines to see how everything all fits, but we have to start being able to do this in our head now, our collective head. Okay, we have multi-headed people here as we are all thinking through this together. So, can you see then let's go back now to our proof and see if we can understand this step of the proof. Here we go. Okay, so here we are back to our proof. Now can you see what's on the next line? It's going to be the P is E equals F, and the Q is E with Z replaced by E, and the R is E with Z replaced by F. I know that's a lot of verbiage, but can you see it? Here it is. It's E equals F implies E with Z replaced by little e equals E with Z replaced by little f. Are you with me? Okay, and now what we're going to do is we're just going to replace equivals with equals because we know that they have the same truth table, right? So that's a legitimate step, okay? So when we replace equals with equivals, we'll have E equals F implies E with Z replaced by E equals E with Z replaced by F. And now we just remove unnecessary parentheses and voila! What do we have? We have a previously proved theorem, namely, which is 3.83. Now, the next topic in today's lecture is a proof technique, a proof style, kind of a new way to prove implications with 3.82, which we will take a look at in a moment. But in order for us to get prepared for this concept, let's go and see what we have and see what we know about algebra proofs involving equality and inequality. And so here is a scenario for us to consider. Suppose you know that A equals B, and that B is greater than C, and that C equals D. Okay, suppose you know these three things. What can you conclude about A and D? Well, because greater than and equal to are together transitive, or we will explore this little concept in a little more detail in a minute. Because greater than and equal to are together transitive, you can prove that A is greater than D like this. Now, we're going to structure this little algebra proof the same way we do our propositional calculus. So here's the proof. Here's how the proof could go. We could start with A, and then we could say that equals by the hint A equals B. So suppose we know that A equals B. So we know that A equals B. So that's how we would write it using this style, this calculation logic style. All right? But what do we know about B? We know that B is greater than C. So now look here. On this next line, we don't put equals, we put greater than. And the hint is that B is greater than C. So you see what, therefore, on the next line goes C. So we know that A equals B and B is greater than C. And therefore, what do we know? Because greater than and equals are together transitive, what do we know at this point? We know that A is greater than C. Because if A equals B and B is greater than C, A has to be greater than C, right? And then for the next step, if we know that C equals D, then D is on the last line. Now what have we shown here? We have shown that because A equals B and B is greater than C, therefore A is greater than C, and then we said that it's because A is greater than C and C equals D, then A has to be greater than D. So you see, we could extend this proof with several more numbers, provided that each number, each time in the string of comparisons, the operation is greater than. If A, for example, I'll just say it, see if you can visualize it. If we know that A equals B and B is greater than C and C equals D and D is greater than E and E equals F, then we know that A is greater than F. You see, we can string them together because greater than and equals are together transitive. All right, so you could have greater than in more than one place. All right, now, in the same way, so now here's 3.82. Now, in the same way that equals and greater than are together transitive, implication and equivals are also together transitive. This 3.82 is transitivity. We could call this together transitivity. So let's take a look at each one of these lines in turn. 3.82a. If P implies Q and Q implies R, then P implies R. So do you see how that's transitive? If P implies Q and Q implies R, then P implies R. But it also works if one of those implications is equivalence. If P is equivalent to Q and Q implies R, then P implies R, just like it did on 3.82a. And furthermore, if the first one is implication, but the second one is equivalence, it's the same thing. In part C, if P implies Q and Q equivals R, then P implies R. So you see, you can think of this, you can think of the implies like greater than, and you can think of the imply, and you can think of the equivals as equals. And it works, but now you have to be careful whenever you do that, whenever you use this technique. Because here, let's go back to our numbers. In this example, suppose you know that A equals B, and you know that B is greater than C, and you know that C is less than D. You don't know anything about A and D. You see, the transitivity doesn't work if one of those goes the other way. Now, with implications, it's the same rule. If you know that P implies Q and Q implies R, and R equals X and X implies Y, you know that P implies Y. But so you can have implication in one direction only. You know what this is like? This is like having a proof with an equivals in it, and you instead of getting the whole thing to a previously proved theorem, you can start with the left-hand side and get it to be equivalent to the right-hand side, or you can start with the right-hand side and get it to be equivalent to the left-hand side. Well, it's the same way with the implications now. So now here's what you can do. To prove an implication, you could start with the antecedent and get it to imply the consequent, or the other way around, you could start with the consequent and get it to follow from the antecedent. Now in this proof, the antecedent, we're going to prove 4.2, right? That P implies Q implies P or R implies Q or R. Now, so the antecedent is P implies Q, and the consequent is P or R implies Q or R. So now there's two ways to do this. We could either start with P implies Q, the antecedent, and get it to imply the consequent, P or R implies Q or R. Or we could start with the consequent, P or R implies Q or R, and get it to follow from the antecedent, P implies Q. Now, do you remember this heuristic? Which side do you start with when we are dealing with equivalence? And we have a choice to start with the left-hand side or the right-hand side. What side do we usually start with? Do you remember? It's the side with the most structure. So using that heuristic, which side should we start with? The consequent. We should start with P or R implies Q or R and get it to follow from P implies Q. Well, that was a lot of verbiage. Sorry about that. Let's go ahead and do the proof. Okay, here we go. We are starting with the consequent, and because we just are starting with the consequent by itself, we don't need the parens, right? So we have P or R implies Q or R. All right, so now here's the first step of our proof. 3.57. Now, we had better take a look at 3.57 because this is not our old friend 3.59. So let's take a look. Okay, here is 3.57. It's an axiom, a definition. It is the definition of implication. P implies Q equivals P or Q equivals Q. So now let's remember this before we go back to our previous slide. So it's the antecedent or the consequent equivals the what? The consequent. All right, so it's the antecedent or the consequent equivals the consequent. Okay, let's go back. Okay, so what do we have here? Here is our first line of our proof. It's the antecedent or the consequent. So what is that? That's P or R or Q or R. And because they are all ors, we don't need any parentheses, right? And what does that equivalent? The consequent, which is what? Q or R. Can you visualize it? Boom. Okay, now what do we have to get this to? We have to get this to a P implies Q. We have to get this to follow from P implies Q. So we have, we've got some R's in here. What are we going to do with these R's? Well, there's two R's on the left-hand side, right? Can we combine those? I think we can. Let's take that R or Q in the middle, and let's just do the symmetry in our head, right? So that would be P or Q or R or R. Now, do you remember R or R? R, R, R. 3.26. Do you remember what 3.26 is? Look it up. I don't think I'm going to take the time to go back. It's idempotency. Do you remember what R or R is? It's by 3.26. It's R. So we have P or Q or R equals Q or R. Now, sports fans, do you remember how to factor out or distribute how disjunction distributes over equivalence? Do you remember that one? Maybe we better look at that one. Here, let's go back. Okay, here it is, 3.27, axiom, distributivity of disjunction over equivalence. So you see we have P or parentheses Q equivalents R equals P or Q equals P or R. Now, the thing of it is that by symmetry, the left-hand side of that equivalence could have been parentheses Q equals R or P equals Q or P equals R or P. Okay, so we can just do the symmetry in our head. By now we should be able to do symmetry and associativity and things like that in our head and not have to write down the explicit steps. So let's go back to our proof. So here's our proof. So do you see what we're going to do is we are going to use 3.27, which is that distributivity. And we are going to factor out the R. So you see, because we have an R or R on the left-hand side and an or R on the right-hand side, we can factor it out. In other words, distributivity is going the other way. All right, so that's our distributivity. But now look, now we have P or Q equals Q. Does that look familiar? Isn't that 3.57? So by 3.57, what is that the same thing as? That's the same thing as P implies Q. So here we have P implies Q or R. And now we get to the key concept of this proof style. Now what's going to be on the next line? Is it going to be an equals? Is it going to be an implies? Or is it going to be a follows from? What do you think? Well, and furthermore, how are we going to get rid of that R? I think this has to do with some kind of a weakening or strengthening. Do you remember how the weakening, strengthening theorems? Here, let's go back and look. Here are the weakening, strengthening theorems. And the key theorem here is 3.76a, weakening the consequent. And what does it say? It says that if P is true, then P or Q is true. But going the other way around, what it says is that another way of saying it is P implies P or Q. But going the other way around, we can say P or Q follows from P. Okay, do you see how that works? P implies P or Q is the same thing as saying P or Q follows from P. So basically what that says is that if you have P or Q, you can just drop the Q and it follows from just one of them. So that's what we're going to do. Here we go. So you see here we have P implies Q or R. So what does that follows from? That follows from P implies Q, because we can just drop the or R. So here we go. Follows from, by 3.76a, P implies P or Q. Of course, what we're doing here is that we are doing 3.76a with P comma Q replaced by P implies Q comma R. So here again, we have to kind of get the facility of being able to do these steps in our head, our collective head. And so what does that follow from? P implies Q, and we are done. Actually, I didn't need the parentheses around that last P implies Q. So now so do you see how mutual transitivity works here? Because the first line equals the second line, and the second line equals the third line, and the third line equals the fourth line, and the fourth line equals the fifth line, and the fifth line follows from the last line. Therefore, the first line follows from the last line. In other words, P or R implies Q or R follows from P implies Q, which is the same thing as saying P implies Q implies parentheses P or R implies Q or R. And we are done. Good deal. See you next time.